So today I want to talk about the last concept that we have for unit number two, and that's finding the inverse of a function. So there's a lot of things. So basically, inverse basically reverses another relation. So what's the inverse of a relation? Well, sometimes it's a function, sometimes it's not. So basically, what is the inverse of a relation? It is a relation that can be a function that reverses another relation. Right? Makes sense. So a lot of times we write this as, and one way you can write this when it's a relation, you write it as r to the negative one. That means inverse. Negative one means taken to the inverse. So here is a relation. It could be a function. It looks like it's a function. So its inverse literally looks like this. Its inverse. Actually, I'll put it in a text box. Its inverse is literally just changing places with x and y. That's one way how you can think about it. It's literally changing places with x and y. So its inverse is negative 7 comma 0 comma 2 comma negative 1, right? And negative 2 comma negative 4 and 3 comma 6. Now, it could be this relation could be a function, but I don't know, but that's it. That's how it goes. Now, what they talk about, you've heard this before, it says a one-to-one function. All right. An easy way to figure this guy out, a one-to-one function is defined as a function is one-to-one if the relation and, that's very important, its inverse are functions. So however you figure that out, that's up to you. I always tell you that you could, we talk about the vertical line test. If a function passes the horizontal line test as well, then its inverse is also a function. Then its inverse is also, whoop, that's funny. Its inverse is also a function. Okay, so kind of be fast with this. All right, this guy passes the vertical line test. Is its inverse going to be a function? Yeah, because it passes the vertical line test. All right, so that's a yes. This guy number two, this thing is a function, but if I run a horizontal line, this is not a one-to-one function. So this is definitely, that means its inverse is not a function. So it's not a one-to-one function. Is this guy a one-to-one function? The answer to that is yes. Yes, it is. Because we know it's a function because it passes the vertical line test, but its inverse is also a function. So yes, it is one-to-one. How about this guy? Is this guy a one-to-one function? Yes, it is. This right here, no, it is not. It fails the horizontal line test miserably. And then this is a relation. It's definitely not a function at all because it fails the vertical line test. So remember, the key to being a one-to-one function is it's got to pass both the horizontal and vertical line test. Now, when you deal with this, if you have a function and its inverse is also a function, we write it with an f to the negative 1. That is awesome. Now, here's the crazy thing. Not all functions have inverses. Sometimes you got to tweak it a little bit. So like if we look at this guy right here, f of x equals 4x minus 8. If I want to find its inverse, I literally trade places, like that f of x is the same as y. So I'm going to retrade places with x and y. And now we solve this for the letter y. So I'm going to add 8. And I'm going to divide everything by 4. So I could write this as x plus 8 over 4 equals y, or I could write it as y equals 1/4 x plus 2. Now that, ladies and gentlemen, we know is a linear function. So I would just say that f to the negative 1 of x is that, right? Make sense? If we look at number 8, so to speak, if you look at number 8, if we trade places with x and y, you trade places with x and y. So this is x equals 1/2 y cubed minus 1. So I add 1 and I get that. Then I'm going to times everything by 2. So if I times everything by 2, I get 2x plus 2 over here equals y cubed. Now, how do I undo something that's been cubed? I take the cube root. So I take the cube root of 2x plus 2, and that's equal to y. Now, is that a function? I believe that's a function. That's a cube root function. You've seen that before. So I could write it as f to the negative 1. That is, in fact, a function. And realistically, there is no restrictions in this domain because it's the cube root function, and we've talked about that before. Now, if we look at this guy, x squared, x minus 4 squared plus 6, we could trade places with x and y, right? Um, but this guy, well, it says determine if f of x has an inverse. If yes, find it and state any restrictions of the domain. I could trade places with x and y and go through and do this, but I can tell you right now that this guy is a parabola. This guy's graph, if I graphed it real quick, would look something, I don't know, like that, and that fails the horizontal line test, so there is no inverse. Okay, so what I want you to do is I want you to take some time. I want you to pause the video, do a couple of the examples, and I'll see you back here, and we'll talk about verifying inverses. Remember, you look for restrictions in the domain if they are. So you can always use decimals to graph it. So to verify if a function, if verifying inverses, to verify if two functions are inverses, then they have to, there's a couple things. One, they are reflections of each other with respect to the identity line. So two functions are inverses if they are reflections of each other in the identity line. That is, the line, like the mirror line that you have would be the y equals x line. Okay, so what do I mean by this? So this is what we're going to do. We're going to do a couple things. First off, we're going to find the inverse of 3x minus 6. So I'm going to trade places. So I'm going to say that's x equals 3y minus 6. So I add 6. I get 3y and divide by 3. So y is equal to x plus 6 over 3. Now I know that that's an inverse, but I got to verify it. So I already know this because I've done this before, but check it out. This is how you verify it. If I open up decimals, and I had this from a previous thing, open up decimals and I type in y equals 3x minus 6. I get this guy right here. Then if I type in my inverse that I found, which I said was, and the cool thing about it is I can say y equals, and what did I say it was? X plus 6 all over 3. You don't have to make it perfect. X plus 6, not x equals 6. Now, I don't care that these guys intersect. What I want you to see is the y equals x line. And the cool thing about it is this is your mirror line. Are they reflections of each other? So what do I mean by that? If I go right here and I click on this point 0, 2, if I go straight across perpendicular, I should have a point -2. I should have a point 20, right? So these guys are reflections. If I select this point right here, 9, 5, there should be a point, or excuse me, 5, 9 on the other one at 9, 5, it should be another one. And there is, it's close enough. So they're reflections of each other. This one, I don't know. Maybe if we take a look at it, we trade places, we know that's a function, and its inverse is probably going to be a function as well because it passes the horizontal line test. But if we trade places, we say x equals y cubed plus 4, right? Then you subtract 4. So x minus 4 equals y cubed. So then the function is going to be the cube root of x minus 4. Now, verify this graphically. So if we go right here, we clear this one out and we clear that one out. I'm going to leave the y equals x line so you can see it's a mirror. I'm going to say y equals x to the third power plus 4. And then I'm going to type in the cube root. So to do the cube root, I think I have to go right over here somewhere. So the question is, how do I put in the cube root? So I can say right here, I can say y equals, and now the cube root, you're going to have to go into functions, and you're going to have to go into miscellaneous, and then you got this guy right here. So then I'll let you put the cube root in, and I'm going to say the cube root of, what is it, x minus 4? X minus 4. And then you can see that this guy does have, they are symmetric with respect to the identity line. So that's kind of, you want to graph this, pick some points, and kind of regurgitate this graph into your thing here. But now when you look at a way you can do it analytically, is the idea for this is that two functions are inverses, right? Two functions are inverses if f of g of x equals g of f of x. What do you mean by that? Well, if f of g of x equals g of f of x, then you're good to go. So what do I mean? So so for this one, let's find f of g of x, and let's find g of f of, that's messy. Let's find g of f of x as well. So let's find the first one, f of g of x. So I'm going to take x minus 7. No, I'm not. I'm going to take 2x plus 7 minus 7 all over 2. So I get 2x over 2. So that cancels out. I just get x. So f of g of x is 2, it gets you x. Let's find g of f of x, g of f of x. If we find g of f of x, then I'm going to find 2 times x minus 7 over 2 plus 7. That 2 cancels. Negative 7 plus 7 goes away. I get x. So f of g of x and g of f of x works. So they are, in fact, inverses. Okay, so I want you to try that. Well, let's do one more. Let's do number. Let's do number 4. All right. So if you find this, you got to find f of g of x. So if we find f of g of x. If we do that, if we find that, we're going to say you take the square root of x plus 5 squared minus 5. So square root of x plus 5 squared is x plus 5. And x plus 5 minus 5 just gets you x. Now let's find g of f of x. All right, now let's find g of f of x. So that is the square root of x squared minus 5 plus 5. So what does that get you? The square root of x squared, which gets you x. So yes, they are in fact inverses of each other. Pause the video, try the other example. Okay, so for the rest of this, this is really just a culmination of everything we did. They want you to do it both ways. They want you to find this guy's inverse, verify it graphically, which I showed you how to do it in decimals, and then verify it algebraically, find f of g of x. This will be extremely beneficial for you to help you with the practice problems. So I know this video also went a little long, but it is quite detailed. But I'll see you again real soon, and may the force be with you.